That's great. But
I haven't seen it in years.
I have the PDF.
Okay, get started.
Yeah.
Sorry,
Guys,
Oh, okay.
sorry. Okay, so we're delighted to have Netta Engelhardt from MIT, and she's going to be telling us about the breakdown of predictability in quantum gravitational collapse.
Thank you very much. You can probably tell I gave an identical seminar at Rutgers yesterday. So thank you for the invitation. It's a pleasure to be here, even if it's only for just a few hours, thanks to various travel hazards. Today I'm going to talk about an upcoming work with my student Lisa Yang and my postdoc Evita Verheigen on a very old problem in classical gravity. The problem of predictability, or also known as the problem of the cosmic censorship. So I'm going to begin this with a somewhat non-traditional motivation. Cosmic censorship is normally motivated from various classical considerations, but I do quantum gravity, so I'm going to motivate cosmic censorship and what it is and describe it and define it from the perspective of someone who's a quantum gravity practitioner. So there is some conventional wisdom that you see if you go to a lot of high energy theory talks, quantum talks on quantum black holes, which is the typical high energy states in quantum gravity are black holes. This is sometimes said explicitly, usually assumed implicitly. I've started taking pictures at various talks whenever I see this being said or stated in some way or other, because it's kind of ubiquitous. That's okay, take it out. Okay. It's a ubiquitous thing that we just say, and a lot of modern understanding of the quantum and semi-classical aspects of black holes is predicated on this accepted lore. And what do I mean by that? For example, black hole thermodynamics, the idea that black holes are thermal systems, the Bekenstein and Hawking discovery, the idea that a black hole interior is describing a bunch of microstates, and the black hole exterior is the way in which they're all identical as a thermal ensemble. We have a lot of results on this, and this underlies and the underpinning of a lot of progress in quantum gravity in the past few decades. Black hole microstate counting, so work starting with this very classic paper of Strominger and Vafa. And more recently, there's been a lot of work understanding chaos and scrambling of black holes. All of this is consistent with the behavior of typical states. And the explanations that we have for all of these are essentially that black holes are typical high energy states. They look like microstates of thermal ensembles. This is why they behave in this way. Now, even though we often assume this, even though it's stated, sort of implicitly assumed in pretty much all of the literature, I would say this is a conjecture. It's at best a conjecture. So why do I say that? This is sort of a very accepted piece of lore. Why am I saying it's at best conjectural? Well, for one, while we do have theorems that guarantee the existence of singularities, the celebrated Penrose singularity theorem, the Hawking-Penrose singularity theorem, and a number of others, there are actually no theorems that guarantee the formation of event horizons in broad generality. Very little is actually known about how prevalent event horizons are in gravitational collapse in dynamical scenarios. So a situation like this, where we have some nice initial data slice, which is asymptotically flat, and we get a time-like singularity forming outside of any horizons, this in principle could be completely generic. And we don't have any theorems that rule that out, and we don't have any indications, any counterindications, other than this accepted lore that black holes should be sort of typical states and therefore generic. So this type of thing bothered people for a long time. The idea that there might be singularities that exist uncloaked by horizons, and naked singularities. This is something that people have wanted to exclude as a possibility, at least as a generic phenomenon in gravity for a very long time. And it has a name. It's called the weak cosmic censorship conjecture, which was formulated sort of fancifully by Roger Penrose as nature abhors a naked singularity, and more formally by Horowitz and Garrosh in 1979. And again, it's this idea that the gravity should be sort of boring outside of event horizons. And there are many different ways in which you can motivate something like this. You could say, okay, to our knowledge, we haven't seen a naked singularity out in the universe. So maybe that's,
So because I don't know the statement, the hypothesis of the conjecture is that the initial conditions are somehow in some
Regular,
sense,
yeah, you're demanding regular.
but also generic.
Generic,
Generic.
that's right. So what you want,
doesn't-
so we know you can fine tune the initial data to create something like this. The question is whether there's it's a set of solutions that result in something like that is not measure zero. So can you slightly perturb it and maintain the singularity there?
Because
And then-
otherwise counterexample exists.
Yeah, so the proposal is that if you slightly perturb this, then it disappears. It maybe collapses into an event horizon or something else that hides the singularity. Yeah. So so there are many good reasons to believe that this is something that could hold. We haven't, to our knowledge, we haven't seen a naked singularity, although we don't really know what that would look like. Another piece of evidence in favor of something like this is that both the Schwarzschild black hole and the Kerr black hole are stable under perturbations. So it's not like you could do something to them and then, kick them a little bit and generate a naked singularity. So that also appears to be that those black holes are somewhat stable, which is nice. And people say, oh, GR should be kind of like deterministic, right? It's deterministic outside of the event horizons. That's kind of roughly what we see in the universe around us. But it turns out that the weak cosmic censorship conjecture is actually false. So as well motivated as it might seem from the perspective of classical gravity, and I have my own doubts about how well motivated it really is, but for a long time people thought it was well motivated, and then it started coming up with counterexamples. So the first counterexamples that you can write down with it, you can write down a Lagrangian with the theory, it satisfies, the null energy condition and so on, was this Gregory-Laflamme instability. So this is something that happens in higher dimensions in pure gravity, where you can take something like the Schwarzschild black hole and extend it along a plane. So you get a black string where if you cut it perpendicular to the string, you get a Schwarzschild black hole in every cut. And you can show that if you take this thing and you slightly perturb it, the perturbation will cause this the ripples like this, and eventually these ripples will sort of pinch off. And in the moment of pinch off, the event horizon bifurcates to reveal the singularity. So this is an example where we can actually get naked singularities and they appear to be generic.
But were you saying they were like transitory?
Well, we don't know, right? We don't know because we can't evolve the system using the Einstein equation past the bifurcation. We don't know how long they last for. There's a hope that maybe, they just gone in an instant, but we don't know. We need quantum gravity for that. What you might say about this is that this is not so bad for the following reason. There's an event horizon to begin with. So the event horizon was sort of also generic, in addition to the naked singularity happening. So maybe this is a situation we can kind of live with. This doesn't invalidate the idea that event horizons are typical, because you start out with an event horizon in this scenario. But so for some time, people thought maybe this is okay. But then we got more counterexamples. So these are charge solutions in 4 dimensions. So not just in high dimensions, but now we have them in 4 dimensions as long as we're asymptotically ADS. And this is just standard Einstein-Maxwell. And you can get singularities that appear to form without any horizon at all. They're just unboundedly large curvatures that do not appear to have any kind of event horizon. So this is a problem. And we also have this more and more, we just keep on getting a catalog of more of these. We can also support this with scalar matter in ADS4. This is again matter that satisfies the null energy condition. There's nothing obviously wrong with it. And there's a very speculative mechanism that might work to generate a counterexample in 4-dimensional asymptotically flat space. So it appears to be the case that weak cosmic censorship is just not true, even though it was very well motivated from the start.
Are these generic?
And sorry?
Are all these counterexamples?
Yes, all of these are
generic?
real counterexamples in the sense that they're generic.
So you start with a Cauchy surface.
You start with initial data and
Initial data that are smooth based on.
that's right. You show that it's for the parameters, you have some open set of parameters that you can choose that all lead to the singularity. Yeah. That's right. And I should add a 4th one here, which is not classical, but is also one we think exists in nature, which is evaporating black holes. Evaporating black holes also are expected to have a naked singularity at the end of the evaporation endpoint.
About these counterexamples, have people understood the CFT interpretation?
So this is an asymptotically flat space.
So the two and three.
I will, let me defer that question to the next slide.
Okay.
Okay, so, or not quite the next slide, a couple of slides from now, I'm gonna have a better answer for you. Okay, so what do we have now? We have the situation where we have naked singularities that appear to be generic. And we also have a statement that much of the progress we've made in quantum gravity requires black holes to be typical states. And that seems to leave us with two possible options here. The first is somehow we have to accept that horizonless gravitational collapse is in fact typical in quantum gravity high energy states. In other words, black holes maybe are not typical after all. I'm going to explain in a minute why that's very bizarre, not just from the perspective of we lose a lot of things we thought were true, but just that there appears to be a conspiracy that would have to make that happen. The second option is maybe all of these solutions, this horizonless gravitational collapse, maybe that's something that only happens in classical GR with supported with some matter, but doesn't actually happen in a UV complete theory. So maybe, as we say, these are things that live only in this warm band. And really naked singularities are kind of very atypical in quantum gravity.
I'm sorry, I would have to ask a naive question. Observationally.
Yeah.
Why do you say could all of our black holes be horizon? How would we know the difference from where we
So
sit?
that's the whole point, right? We don't know that. So in order to observe a black hole, we have to wait an infinite amount of time because the horizon is the boundary of the path described.
Fair enough, but there's a whole lot of evidence that we have black holes and so.
I strongly disagree with that statement. The definition of an event horizon is the boundary of the past of I plus. We have no evidence that there are black holes in our universe because it's
Okay.
impossible to collect evidence.
There's certainly
Yeah, we have to wait.
extremely singular regions,
But
but but that's.
I mean, for
You're making
a quantum gravity person, yes, but for instance, there is a lot of evidence in numerical gravity where
Yes.
ipso facto you have genericity because you have errors in the grid and error in the meshes, right? And none of these evolutions create naked singularities.
no, that's
right?
not true at all.
Yeah.
You
I mean,
mean for the simulations of what we've seen in our universe?
In our maybe with a Cauchy surface that does not contain the answer already there, does not contain a horizon.
Well, so the question is,
The second-
what are we assuming about the asymptotics of our universe? If this counterexample works out and we live in an asymptotically flat space, then no, I would say there's an example where we would time evolve generic initial data with asymptotically flat four-dimensional space-time, and we would generate a naked singularity.
But
I
is
think the
that true?
reason-
I mean, this Santos Epron is really proven.
So Santos and Epron gave a mechanism for this to work in asymptotically flat four dimensions flat with that space, but they can't prove convergence. They can only show that it looks like it's approaching something, but they can't prove radius of convergence. So because this is a numerical simulation and they can't prove what the radius of convergence is, that's what I call a speculative mechanism. Because they can't prove that it converges to a naked singularity, all they can show is that it sort of features very similar kind of resonances that you see in these examples, which suggests that maybe something like similar happens here, but without a proof on the radius of convergence, you can't be sure that this generates a naked singularity.
So what kind of matter is required there? Because it's.
Good, so I'm gonna get to that. So I think, so for some of the examples, you need Einstein-Maxwell. This is just an ordinary scalar. For this, I believe in the paper, they use Einstein-Maxwell, but talking to George, it sounds like they also are able to do this with a dilaton. If the radius of convergence works, yeah. Okay, so we have to contend with the following two possibilities. The first is that horizonless gravitational collapse is in fact typical in quantum gravity high energy states. Yeah, question.
I'm so sorry.
No worries.
I'm not a sophisticated in this by any means, but I wanted to know what, so to speak, empirically, would there be in principle an observational way to distinguish between a horizonless collapse and a conventional collapse?
So
Was-
in
is there
order
a
to,
signature?
so a horizonless collapse would be one in which in finite time, we would see something like a singularity forming. We would, what does that look like? I don't know because I don't have a non-perturbative quantum theory of gravity I can write down for you. But there would be, in finite time, we would be able to tell the difference. How long that finite time is, that depends strongly on how far we are from the singularity. So in principle, it is not impossible that every black hole, quote unquote, that we have seen to date is in fact a naked singularity or the locus of some naked singularity, and we just need to wait a bit longer to see it.
But when you say to see it, I don't get what you mean to
To
see
we
it.
literally receive null geodesics from it.
I would like to add a little bit on what Glennis just asked. There is evidence that suggests that, for example, all gamma rays bursts produce a black hole. And that's a collapse that produces a black hole. The evidence comes not directly from the quantum gravity side, but it comes from jets that have a gamma of 500 and things like that and so on.
I think the evidence makes various assumptions about what the definition of a black hole is.
Yes, but it makes various assumptions, but at the end, it says, oh, if it's something else, then it's more complicated than it being a black hole, and therefore I'll adopt a black hole.
I don't, so that makes assumptions. That assumption that that it's something else and therefore must be more complicated.
But let me go to my real question.
Yes, go for it.
My real question is that different from the black holes that presumably are produced in gamma ray bursts, there is at least one example in NGC 6946, BH1, it's called, which is supposed to be a direct collapse of a star to a black hole.
How do you know that?
Because there was nothing else seen that, is normally seen.
But you wouldn't see anything else. I mean, the whole point of a black hole,
But
I think we're disagreeing on.
I still have not asked my question. I still have not asked my question.
There is a black hole here.
There was
but
no
one.
supernova explosion,
What is
okay?
your definition of a black hole?
Okay, no, wait,
No,
wait,
I'd like a definition to answer your question.
but I still not asked my question. The question is the following. That one is a collapse that did not produce a supernova explosion. Okay, so it's different from all other presumed black holes. I'm giving you right now the possibility that none of them are black holes, but the ones in gamma ray bursts are assumed to be black holes. This one is assumed to be a black hole, but which had no supernova explosion and therefore represented a direct collapse. Is it possible? This is finally my question. Is it possible that it's the difference between these direct collapses and things that are produced via supernova explosion
I
that produce?
can't
this
weigh in on
different-
that because in the absence of a non-perturbative quantum theory of gravity that tells me what a naked singularity actually looks like, I can't answer that question. All I'm talking about in this talk is whether those things exist, whether they're generic. And I agree that it seems strange. I'm not saying that I strongly believe that we have naked singularities in a universe. In fact, my goal in this talk is to argue that they shouldn't exist. But there is a very serious theoretical tension between what we see theoretically and what we want to get out of the theory. And that's what this talk is about. So I can't tell you how the naked singularity evolves, what we would literally see if we look at the null geodesics coming from it. But what I'm going to argue nevertheless is that these things are very atypical. But before we get there, how do we, in order to ask how we argue that, we would like to understand what the options even are in the first place, and how do we explain the fact that they appear to be typical in classical general relativity. So again, the first option is they're typical in classical GR, they're typical in quantum gravity, and here we are. We have to somehow deal with that. And the second option is that they're typical in classical GR, but atypical in quantum gravity. Since our universe is fundamentally described by quantum gravity, that would tell us that in our universe, naked singularities are in fact atypical. Now, how do we choose between these two options? And I would say the first option is, it requires some kind of a conspiracy. We already know that black holes behave like typical states. We have a lot of tests of this in the ADS-CFT correspondence. We've seen it in other contexts. We know black holes behave like typical states. So if they're not typical, then somehow naked singularities are really the typical states and black holes are mimicking them, even though they're atypical. Or conversely, naked singularities are exactly typical, mimicking typical behavior that black holes are already showing or illustrating for us, even though the two phenomena are extremely different. So let me say a few more words about this conspiracy. So we say, okay, for them both to be typical, or even for naked singularities to be typical, independently of whether black holes are or not, it has to be the case that naked singularities behave exactly like black holes. Except naked singularities are, they're very different. Typicality of black holes has been linked specifically to properties of the event horizon at adionicity. That's where we sort of argue that black holes are typical. And naked singularities, not only do they not have a horizon by definition, but also they're highly dynamical. So they're not adiabatic, there's no adiabatic evolution, and there's no event horizon. And properties of typicality have sort of been linked to the behavior of the event horizon once everything has kind of relatively settled down. So it would be quite a strange conspiracy for naked singularities to be typical, considering that black holes are very different and are themselves behaving like typical states. So that leads us to preferentially to option 2, that naked singularities are actually typically in this swampland. They don't actually manifest in a classical theory that comes from a consistent that has a consistent UV completion. And there are quite a few pieces of evidence in favor of this. So many of these known examples, and Ivan, this is getting close to your question, many of the known examples of generic naked singularities violate the weak gravity conjecture. So that suggests that, okay, these particular theories that support these naked singularities are in this swampland. But not quite all of the examples do this. Other things we know, and this is related to ADS-CFT now, it's actually possible to prove an inequality known as the Penrose inequality in ADS from ADS-CFT. Just consistency of the very basic aspects of the ADS-CFT dictionary. And what is this Penrose inequality? It's an upper bound, it's an inequality that relates the area of minimal surfaces to the asymptotic mass. And it's actually a necessary condition for cosmic censorship to hold. It's not sufficient, proving it is not tantamount to proving cosmic censorship, but it's strong evidence that some version of weak cosmic censorship holds. And finally, it's actually possible to violate this inequality with very ordinary looking matter fields. But if you take a potential for these matter fields in the Lagrangian and you start dialing it, dial some parameters, when you get to supergravity, magically the Penrose inequality is restored. And as soon as you start dialing the parameters away from supergravity, the Penrose inequality is violated. Which again is very suggestive that in a theory with supersymmetry, that nice UV completion, some version of the cosmic censorship conjecture that naked singularities are non-generic appears to hold.
Can you
Okay.
remind us which consistency of the dictionary?
Sorry,
Can you remind us which consistency of the DSFT you need to prove Penrose?
remind you what which
Just say
aspect
that-
of the dictionary?
Yes.
This uses the to prove the inequality, you use the Ryuta-Kyanagi. You can prove this statement here, which is also a version of the Penrose inequality in a sense. You can prove that trapped surfaces have to lie behind horizons. And for this, you don't have to prove Ryuta-Kyanagi. You don't have to use Ryuta-Kyanagi so much as you use okay, what you're really using here is unitarity of the boundary theory. So as well as a couple of assumptions about the bulk. So none of these are conclusive, but they're all kind of very suggestive that the quantum gravity theory is sort of what better behaved than the classical theory would suggest.
So when you quoted evidence against the conspiracy, you did not mention that in ADS-CFT, both the generic density of state in the CFT and the generic density derived using Mackenzie-Hawking agree.
Yeah.
So there would be
But
another
that's one of
couple
the black hole thermodynamic statistics. Yeah, there's a lot of evidence in ADS-CFT that black holes must be typical in high energy states. Yeah. Okay, so you might be tempted to just accept this perspective and say there's no problem with it, but it's not quite that simple. Evaporating black holes are in fact expected to end in a naked singularity, so it's not like we can just say quantum gravity doesn't want to have naked singularities because quantum gravity wants black holes to evaporate. So we expect that some kind of naked singularities can in fact occur in typical states. And these pinch-off or Gregory-Laflamme type instability also seems kind of robust in quantum gravity too. It's pure gravity in higher dimensions. There's no reason to exclude it. So it doesn't seem like we can do away with this one. And then there's also the certain time-like singularities that admit a resolution in string theory, like the 60 Oriental fold. where you can resolve it without having any access to non-perturbative quantum gravity. In the orientable case, you do an uplift to M theory. So that means that those singularities certainly, those time-like singularities certainly have a right to exist if we subscribe to the idea that string theory and the UV completion of string theory is actually describing quantum gravity in some realistic, potentially realistic universe. Question?
Quick question, for the evaporating black holes, it does sort of the asymptotic matter, because asymptotically flat ADS.
So for the evaporating black hole, it is I have not subscribed to particular asymptotics yet.
Okay.
Of course, we can't evolve the black hole all the way to the evaporation point, but we sort of expect that at the evaporation point there is a naked singularity. We can't prove it.
Okay.
Yeah. So it seems that there are some naked singularities that are actually okay, and some naked singularities that would not be okay. So there's a bit of a zoo here. So I would say that there are really three categories of naked singularities that we need to worry about or think about. The first are naked singularities that appear before any event horizons have formed or independently of event horizons, and can only be resolved in full non-perturbative quantum gravity. So that's one category. That's the category of most of the counterexamples that I talked about. The counterexample of in ADS4, the counterexample of Einstein-Maxwell, and so on.
When you say resolved, what did you mean exactly?
So in this case over here, so I'm going to talk a little bit more about this, but specifically I had in mind something like if you have like a D brane that looks singular from the classical GR perspective, but we understand it in ordinary string theory without having to talk about the non-perturbative UV completion. So it's anything that you can explain or sort of evolve through without access to full non-perturbative quantum gravity. So oriental singularities are sometimes of that nature. And that's the second category. So some singularities can be resolved without access to non-perturbative quantum gravity, and then they certainly seem like they should be physical. And then singularities that appear as a byproduct of black hole evolution, regular Laflamme type instability and the evaporating black hole. So it appears that we have sort of three categories. And really the only one that would give us a real problem with asserting that black holes are in fact typical high energy states would be the first one. This is the one that we don't want to be typical. The other two sort of don't seem to be particularly problematic. So we would like to argue that horizonless singularities are atypical unless they can be resolved without access to full quantum gravity. And I say horizonless, I mean ones that do not form as a consequence of the natural evolution of event horizons. Now, this is the notoriously difficult problem, cosmic censorship. And part of the reason is that singularities are hard to talk about. The definition of a singularity is very classical. We define singularities as the existence of an incomplete, inextendable null geodesic, or not necessarily null, but can be time-like or even space-like if you like, but the existence of an incomplete, inextendable geodesic. That's an extremely classical definition, but we're talking about a situation where effective field theory has broken down. So this definition is not particularly useful for understanding the behavior of singularities and quantifying things about them. So this, in particular, singularities, they signal a breakdown of the predictivity of the effective semiclassical description. And this can happen even in parts of the space-time where the curvature is low. You have a Cauchy horizon that goes all the way out to infinity, and you have a breakdown of predictability of the effective field theory, even though the large curvatures are localized in a very far away region of the space-time. So here's the example. You have a naked singularity here. It's an ADS collapse. And we're sitting over here, and effective field theory can't tell us what's happening anymore, even if curvatures are extremely low. So you need boundary conditions from quantum gravity to evolve through this object. Okay, so what we're going to do is, to begin with, to just tackle this problem, is give an operational definition of a singularity that's not in terms of the incomplete geodesics, but in terms of the failure of predictability of the effective theory. So we're going to assume that there is some asymptotic, some time evolution in the fundamental description of the system. I have this asymptotically flat picture here. I'm going to mostly work in ADS CFT, but in fact, almost everything I say will generalize to, under certain assumptions, to more general relation between fundamental quantum description and the semi-classical description. But for clarity, I'm going to try to work mostly with ADS CFT. So let's assume that there's a fundamental notion of time evolution in the system. If we have an asymptotic boundary, that's given for us, the asymptotic time evolution. If we have a closed universe, I'm agnostic about that, whether there does or does not exist some continuous time evolution in the fundamental description. And let's consider an operational description. We're getting an operational definition of it. So we're gonna consider a semi-classical experimentalist. And our experimentalist is gonna be living in the low curvature region of space-time, not necessarily asymptotic, just anywhere in the low curvature region. So for a black hole, includes the black hole interior until you get close to the singularity. And for naked singularity, just gonna stay away from this near singularity region. Now, our experimentalist is going to make a bunch of measurements on the system. For example, you can imagine doing scattering experiments, scattering something off the singularity if you're here, just a scattering experiment when you're inside the black hole. And I'm going to demand that semi-classicality means that we're restricted to not doing a number of experiments that scales exponentially with GH bar. That seems like a very reasonable definition of, not non-perturbative. Now, so here n you can think of as the n in ADS CFT, or you can think of it as a stand-in and dimensionless parameter I defined using GH bar. Okay, so I think the Zoom is hiding the bottom of the slide. Is there a way to get rid of it by any chance? The meeting controls? I can talk in the meantime. So, okay, so an experimentalist is able to make all of these measurements up to a number which is very small compared to something that's exponential in one of a GH bar. And the experimentalist is then going to process this data. And they're going to be able to process this data for a time which is short compared to an exponentially long time in GH bar. So it's okay, we can, all right, so it's fine. So this is supposed to say short, oh, there we go. Short compared to time to scale exponentially with the system size, which goes as 1 over GH. So again, this is just to keep things semi-classical, no access to things that are exponentially large in the quantum gravity coupling. All right, then our experimentalist is going to morph into a theorist, which is, perhaps the least believable part of this. And the goal in life of the theorist is to produce a prediction for the time evolution of the system. So time evolution operator O, we're going to try to produce a prediction for what that is. So the theorist is going to produce some guess, O guess, that successfully reproduces all of it. So if the theorist manages to produce a guess operator, O guess, that successfully reproduces the expectation values of all of the operators in the system under the actual time evolution, meaning if the expectation values of operators under time evolution by O guess are approximately the same as this should be an O here, and the expectation values of operators under the true time evolution, then we say the semi-classical theory is predicted. Now, this should be O, I don't know what happened here. We say that O is predictable. And I want to emphasize something here. This is not the same thing as using the equations of motion of the semi-classical theory to keep on evolving. This is about feeding the semi-classical theory the outcome of experiments and then asking if it is possible to make a prediction for the time evolution. So it's possible, so predictivity defined in this way can persist after the semi-classical theory has in fact broken down. And I would say situations like the 6D Oriental fold or D-branes fall under predictivity. You can't evolve the Einstein equation beyond those, but you can certainly do something that doesn't involve exponential computation to figure out what the time evolution needs to look like. Now, if the theorist fails at producing such a guess, if the theorist's guess, no matter how hard they try, fails to reproduce the expectation values of operators under the true time evolution, then we say that semi-classical theory loses predictivity of the system. And what we want to rule out is the possibility that loss of predictivity without horizons is typical. We do not want that to happen. So here's the formal definition of predictivity. So the evolution O of a system of size log dim h plus n. H here is the quantum gravity Hilbert space. This is predictable if there exists a quantum algorithm. A modeling theorist does quantum algorithms that run in a time that's no longer than polynomial in n, and which queries the system, meaning makes measurements on the system, for no more than polynomial in n times. And then the algorithm attempts to guess an operator O guess that satisfies this property in the large n limit. If this is successful, it's predictable. Otherwise, the time evolution is unpredictable.
So this is a case in which quantum gravity is simpler than quantum field theory.
So sorry?
This is a case where quantum gravity is simpler than quantum field theory because
yes.
n is infinite. Right?
Well, so we actually, one thing we ran into is we want to talk about a classical limit. So we do end up having to take a very careful limit of the n goes to infinity case. But it's nice that we can work occasionally with finite n. Yeah. Okay, so what is the goal of this talk? So now that I'm about half an hour into it, I can tell you what the purpose is. So the goal is to give an argument, and the technical details are in a paper that's, I'm hoping will come out next week, which means it'll come out 2 weeks from now. That the failure of predictivity prior to horizon formation or in the absence of horizons is atypical. So the probability of unpredictability that's not a result of black hole evolution is going to be extremely suppressed, exponentially suppressed in n. And if you take the n goes to infinity limit, that means the probability goes to 0 with strong prejudice. So how do we do this? We're going to heavily rely on one primary workhorse, which is equivariance, which I'll explain now. Now, as I said before, I'm going to present this argument in the language of ADS-CFT, and then I'm going to describe it towards the end, the way in which some assumptions are reasonable to make more generally, and equivariance is probably one of them in the context of asymptotically flat space, although possibly not in the context of closed universes. So what we need is equivariance of the map between the bulk or the semi-classical theory and the boundary or the fundamental quantum theory description. So this is an assumption, I'm just copying to it now. It's an assumption that certainly is true in ADS-CFT and may be true more generally. And I was also going to hold essentially whenever that assumption is satisfied. That's the main assumption. So what's equivariance in terms of like more precisely? So here we have, I'm imagining the bulk or the semi-classical theory is on this side, and the boundary of the fundamental description is on this side. The B is the bulk to boundary map at earlier times. F is the bulk to boundary map at a slightly later time. C is the time evolution in the bulk, and U sub n is a time evolution on the boundary at some finite value of n. Doesn't have to be unitary in ADS-CFT, of course it is. And equivariance is the statement that you can first map from bulk to boundary and then time evolve, or you can first time evolve and then map from bulk to boundary and you get the same thing. There's a statement that time evolution is consistent with bulk reconstruction, and you can weave back and forth between them. This is a core feature of ADS-CFT, and this is the statement. F composed with C is the same as U composed with B.
And C is the exact evolution, not the semi-class.
Yeah, that's right. Yeah. So there's a subtle limit that we have to take here that I'm glossing over in this talk, but it gave us a lot of grief, which is so really what we do is we work at finite n on this side and infinite n on this side, and then there are corrections here that are suppressed in powers of 1 over poly n. So you basically do an asymptotic, you say that this converges asymptotically. This equation is true asymptotically. That allows you to talk about time evolution in the boundary theory, because if you first took the infinite n limit, then you had GFF on the boundary, and that doesn't have a time evolution. This C is inherited from first doing the full quantum gravity time evolution and then taking the infinite n limit. So for example, if you have a naked singularity, we inherit boundary conditions on that naked singularity by virtue of the order in which we took the limits. Okay, so here we are. So suppose that we start off with some nice smooth initial data, asymptotically ADS, call it on the Cauchy slice sigma 1, or sorry, it's not a global well, it's not a Cauchy slice, it's spatial slice sigma 1. And after a little bit of time, it forms a naked singularity up here. Now, if every such regular initial data slice had an event horizon intersecting it, we would be done. There would be no horizonless collapse resulting in singularities. So assume that it's horizonless. Now, at early times, this reconstruction of the data on sigma 1 can be done simply purely using very ordinary tools in causal quantum field theory. Essentially because this causal diamond here, which is the past of T intersecting with the future of T in a bulk, this thing here does not contain any pathologies. It's taken to be so that because sigma 1 is to the past of the naked singularity, it's a completely regular slice with no dependence on the naked singularity. Everything is just local quantum field theory propagating on a curved background. There's no divergent curvatures, there's no event horizons, there's no complications. And what that means is that the bulk to boundary map on this slice is extremely simple. It's essentially just local time evolution. You can just locally time evolve the data either from T down to sigma 1, or you can do something like the reverse of that from sigma 1 to T. And so that's a very simple map. I think I'm going to, so this is actually describing exactly what I just explained in terms of the limits. I'm going to go ahead and skip that. And so this, okay, so the statement that I made earlier, I did not say that here. Okay, so also true, not just, so we have that the bulk to boundary map is going to be simple as long as we're within that wedge that doesn't contain any gravitational pathologies like horizons or singularities. Now, it's also true that at sufficiently short times, the boundary time evolution operator is also simple. And when I say that, what I mean is that it's approximately non-scrambling. Now you could say, I've heard that quantum gravity is a fast scrambler. How could you possibly say that? And the answer is, sure, quantum gravity is a fast scrambler, but even fast scramblers only scramble on times of order log s, where s is the entropy. These are all times of order n to the 0, so not log n, but n to the 0. And we're going to take the times to be as short as we need to guarantee that un is approximately local. So again, not exactly, we know it scrambles over long periods of time, but it's going to be approximately local. And then what we're going to do is we're going to do some quantum information. We're going to write b and u sub n in the Pauli basis. The reason that I'm doing that is because it will turn out to be, there's a theorem in quantum information, quantum computing that we're going to want to use that applies to the Pauli basis. So the Pauli basis is just a basis of operators for any Hilbert base of, well, technically any finite dimension, but you can generalize, give a generalized Pauli basis, infinite dimensions, where this here is a product of single cubic Pauli operators. So any operator can be written as this expansion. This is just a basis. And it turns out that because U is approximately local and B is also approximately local time evolution, that means that they can both be written as a very short expansion in terms of the Pauli basis. In particular, they can be written as an expansion where the non-vanishing coefficients only exist for an order 1 number of products of the Paulis. So normally you can have very, very many products of the Paulis, ones that scale with n. But it turns out when you're approximately local objects, rating k local, then the product of the Paulis here is going to be order 1. So that's something called, maps like this are very special in quantum computing. They're called bounded degree. All right, so I went through this trouble of defining bounded degree. What does this buy us? Okay, so now we're going to consider the system at 2 times, sigma 1 and sigma 2. And we get from sigma 1 to sigma 2 by time evolution c, which is some mysterious thing that we don't know how to write down, but we know quantum gravity provides. There's a time evolution through the naked singularity, and we're going to make absolutely no assumptions about what that is, just that it's some map that exists. We're not assuming positivity, we're not assuming that it preserves traces, nothing. Now, equivariance now comes in. Equivariance tells us that if we do this, that's the same as doing that. We've already shown that B and U are very simple. In particular, B is this bounded degree property, and U has this bounded degree property. And the composition of 2 bounded degree maps is bounded degree. You don't gain order n number of Paulis from multiplying order 1 number of Paulis. So that tells us that B composed with UN is bounded degree, and therefore C composed with F is also, or F composed with C is also bounded degree. And so that means that these can be written again as a very short sequence of or series of the Paulis. And the coefficients of the high degree product Paulis will vanish. So this combination is bounded degree. Now, if F composed with C is bounded degree, there are 2 options. Either F and C are both bounded degree, or C is unbounded degree, which means F is also unbounded degree because they have to cancel to give a total product, which is bounded degree. And now there's a theorem, it's a beautiful theorem by Huang, Chen, and Preskel. Bounded degree maps are predictable by the exact definition that I gave earlier. So that means that if C is bounded degree, then there was no naked singularity there. Or if there was, it was one of those resolvable ones. It's completely predictable from the effective field theory, according to this theorem by Huang, Chen, and Preskel. So what we want to show is that 2 is somehow very atypical. So what we show is that if C is unbounded degree and not predictable, in fact, you can prove it's unpredictable in that case, by this essentially is the converse of this theorem. If C is unbounded degree, we want to prove that there's something very atypical about the function f, which is composing with C to give you exact cancellations of all of the high degree terms. So that's the technical meat of this result. So again, we want to allow for the possibility that non-perturbative quantum naked singularities do exist, but if they do, they have to be very atypical. Right, that's what we want to show. We don't need to show that they don't exist, just that they're extremely atypical. So that means if we start out with a solution that has such a thing, and we slightly perturb it, we want to see that something goes wrong. That it disappears, that there's some inconsistency, that essentially, once we perturb the initial data, we don't get that non-predictability anymore. So let's go ahead and do that. We're going to start with our initial slice sigma 1, and want to perturb it a little bit. And in the language of ADS-CFT, that corresponds to slightly perturbing the code subspace, which corresponds to slightly perturbing the bulk to boundary map, which means that all we have to do is take this map B, bulk to boundary at early times, and slightly change it. So we're going to add some random perturbation to delta B, to B, and ask what happens. So we're going to take delta B to be a random perturbation drawn from some arbitrary smooth distribution. And we're going to take it to be small in L2 norm compared with the L2 norm of the time evolution operator. We just fix one thing and take everything to be small compared to that. And we'll normalize this one to 1. Again, we can multiply it by whatever we need to in order to get this to be 1, and we'll take delta B, the L2 norm of that, to be very small. That's what we mean by a small perturbation. Now, since delta B is random, it's picked at random, it's typically going to have a spread over all of the polys of the low degree ones. It'll typically be some high degree thing, but that's okay. It has very small magnitude, so it'll introduce some very small high degree corrections. That tells us, so if we then compute the overall change to U composed with B, bulk to boundary composed with time evolution, and we ask what is the high degree contributions to that, what's the norm of the high degree of that, it's going to be very small. The interpretation of this is if you take the initial data slice and you slightly perturb it with some random perturbation and then you time evolve, you don't expect that a very short amount of time evolution is going to cause things to blow up. And indeed it doesn't, as we see from this very small change. Before the perturbation, the high degree was 0. Now the high degree is still very small. Now, perturbing the system at an early time by delta B, that will also change the system at a later time. So we can model, so we say, okay, so if UN changes, UN composed with B changes to UN composed with B plus delta B, then F composed with C will also change by a little bit. And it will change by, it's possible for F to change, it's possible for C to change, it's possible for both of them to change. Right, there's some change to the early slice and it'll result in changes to the maps F and C. Now, it turns out that the technical treatment of each one of these terms is identical, but the conceptual treatment of this is easier. So I'm just going to fix C and focus on this one. And you can trust that technically speaking, this follows through for the other terms. Okay, so as for conceptual simplicity, we're just going to ignore the delta C terms and focus on just this one. So we have, okay, delta F composed with C is UN composed with delta B. And since delta B is drawn at random from some distribution, delta F is also drawn at random from a distribution which is related. You can compute the mean and the variance using the fact that U and C are both fixed operands. Okay, so here we have again this picture. So we know delta F is going to be the change to the system after time evolution by C. And we want to see something break when C is unpredictable. Something that equivariance breaks or something goes wrong. So what happens if C is predictable? Let's start with that. So suppose C is predictable. If C is predictable, then essentially it behaves just like U sub n. When we composed delta B with U sub n, we got that, sure, there are some new high degree terms, but they're very small. And if C is predictable, we get the same thing. If C is predictable, then on average among all the possible perturbations delta B, the contributions, the high degree contributions to delta F composed with C are approximately of the same order as the perturbation itself. So you slightly perturb the system, you evolve it for a short amount of time, and you find that the perturbations are still of a similar magnitude as they were before the time evolution, provided time evolution was short enough. That's very consistent. This suggests the system is stable. Now you might say, okay, but this is on average. What if you sort of have two tails which dominate and the average doesn't? You can actually show that it's also true for typical states. So deviations from this average are very unlikely. So for predictable C, we have a consistency here. You slightly perturb the system at early times, it results in a small perturbation of the system at late times. The change to B composed with U is the same as the change to F composed with C in magnitude. Okay, so things are consistent if C is typical, is predictable. Now what happens when C is unpredictable? We'd like to see something break. All right, so again, we have a predictable C, the deviation from bounded degree, this additional high degree thing, is preserved over short time scales. If you don't have a non-perturbative singularity to begin with, we're not going to develop one as a result of slightly perturbing the system. So that suggests that at least predictable states are typical or at least stable. Now suppose C is unpredictable. So that means that it has a very large number of high degree Pauli products divided out in the Pauli basis. That's what it means to be predictive, to be unpredictable. And there's a missing bracket here, but what it's should be another one over here. What we'd like to show is that the average magnitude of delta F composed with C is much larger than the average magnitude of UN composed with delta B, even though those two should be the same under equivariance. So here's the result. We do in fact manage to show that. So, okay, so if we can show it and show first what we would gain. If we can show something like that, that means that you really need to fine tune the perturbation if you're going to preserve equivariance. If you take a delta F, which is a little bit not quite fine tuned, you're going to essentially blow up the high degree contributions to C. So you're going to say, I'm going to take a tiny perturbation and apply it to my system, and the system is going to end up very, very far from where it was, which is a way of saying the system's unstable. So here's what we find. So if C is unpredictable, then on average, the contributions, the high degree contributions to delta F composed with C, which should be equal to delta B composed with U, this is equal not to the magnitude of the perturbation, but to the magnitude of the perturbation enhanced with e to the alpha n in the infinite n limit, where alpha is an order 1 constant. This is vast. This blows up. Doesn't matter how small you take this perturbation. We're taking the n goes to infinity limit. So this thing is going to be huge. And we find that the unpredictable part of delta F composed with C blows up for anything you hit it with, any small perturbation. It's not going to be consistent anymore with equivariance and what you get in the boundary theorem. And in fact, you could worry about this issue where, whoa, what if I have like 2 dominating tails and really the average doesn't really mean anything? You can also actually prove that the probability of a randomly drawn delta F or randomly drawn delta B deviating from this average by more than some epsilon is extremely small, e to the epsilon squared over alpha n squared, so it's exponentially suppressed. So what we have here is the statement that as n goes to infinity, it literally becomes impossible to map the B composed with U to C composed with delta F, if C is unpredictable. You slightly perturb the system a little bit, and it immediately the two become very, very far from one another. So that means that if C is predictable, then the typical delta F, the typical perturbation to the system, it will result in high degree terms, but they're going to be small. The system is stable against perturbations. It matches equivariance. If C is unpredictable, it doesn't matter how small we take delta F. It's going to result in very large corrections. The magnitude is going to be extremely enhanced. So the interpretation is that either initial unpredictable vacant singularities just don't exist, or if they do exist, this should be just once. This is last week we thought it was doubly exponentially small, but it turns out just once exponentially small. And it turns out that it must be an exponentially small fraction of the state space. So that basically any small perturbation of the system must change C in such a way that it becomes predictable. Then you compose C with the perturbation and you get consistency with equivariance. Now, I think, let's see, I guess we usually finish on the dot here.
Yeah.
Okay, so let me just say a couple of words about other ways in which we could imagine doing this, trying to get around this issue. You could say, well, should you really be considering a completely random delta B? Maybe you should consider a delta B that preserves your initial structure. So you started out with a B that was bounded degree. Maybe you should consider a delta B, which is also bounded degree. So let's take delta B to be bounded degree, and we can preserve the initial structure and not have any corrections to it. Then maybe that will actually, allow us to see that naked singularities are typical as long as your perturbations are not fine-tuned so much as just, consistent with the initial structure. But actually now matters are worse. Now, because delta B is exactly bounded degree, this object, because this was bounded degree and this was bounded degree, this whole thing is not bounded degree. And you can ask, what's the probability that this whole thing is bounded degree? And it turns out that it's 0. So it's not even, it doesn't even scale, exponentially, not even suppressed exponentially with n, but the probability that if you would do an exactly bounded degree perturbation to an early slice, that you can match that with a naked singularity is exactly 0. So that doesn't help us, that doesn't hurt us if you'd like to say naked singularities are atypical. And you could try various different sort of versions of this. So you could say, oh, what if we kind of fine tune delta B, but then we say instead of delta B is exactly bounded degree, it's approximately bounded degree. We tried various different ways of making the result robust and making sure that no matter how you manage to motivate the perturbation you start out with, you're still going to find that it can't do the job. No matter what perturbation you start out with, whether you fine tune it to be exactly bounded degree, you tune it to be approximately bounded degree, you take a random perturbation, essentially, no matter what, you always find that the unpredictable C just can't accommodate it. As soon as you slightly perturb the system, the unpredictable C will give you results that are inconsistent with the holographic dictionary. So this is essentially what I just said and kind of glossing over a little bit. Okay. So we have a result that seems to suggest that unpredictable naked singularities are atypical. What does that mean for the original weak cosmic censorship conjecture, which is what we started out with? So under the assumptions I gave, for example, equivariance, naked singularities that form from horizonless initial data and are robust against generic perturbations are going to be in the swamp band, so long as they stay away from the asymptotic boundary. Why do I say that? Situations like this, where we no longer are sure that we have a fundamental notion of time evolution beyond a certain point, do not obviously apply. Because it's not clear how you're supposed to use equivariance if you don't know how to do time evolution in your fundamental description, or you don't know if traditional time evolution exists. So there's this asterisk here, so we can rule out things like this, but we can't rule out things like that, which according to the letter of weak cosmic censorship should also not exist. Now, the weak cosmic censorship conjecture, it can still be violated by naked singularities such as Gregory-Laflamme instability. It can still be violated by the Oriento folds. It can still be violated by evaporating black holes. But we don't have a problem with that because, as I said, I'm motivated by quantum gravity, which is the theory of the real world, and quantum gravity doesn't care about those. That doesn't pose any inconsistency for us. And again, it can also be violated by singularities that do something like this, which I have nothing to say about those so far in this talk. Now, it turns out we can also have a sort of mild comment, I would call it, about strong cosmic censorship. So strong cosmic censorship is a different conjecture from weak cosmic censorship, which is neither stronger nor weaker than the weak cosmic censorship conjecture. Strong cosmic censorship is the statement that time-like singularities do not exist. Whether inside black holes or outside of black holes, they don't exist in generic states. So they're unstable as soon as you perturb, singularity goes away. We can make some progress on the strong cosmic censorship hypothesis. So suppose that we prepare the following situation. We have some initial data slice, which is smooth. And again, we're going to insist that this initial data slice lives entirely within the past and future of some boundary time slice. This is not behind an event horizon, and it's a regular initial data slice. Then we can give the same argument as long as u sub n is sufficiently short on time, in terms of time scale. If we take this to be like as a scrambling time, so if a black hole forms and we take this to be the scrambling time, un is not bounded degree and we cannot make the argument. But for short enough time scales, very early collapse stages, we actually can have the same statement, which is on very short time scales, no system can be, arbitrarily fast scrambling, fast scramble, scramble, and order log to the s, a log of s, which means that we can put a bound on how early a time-like singularity can form if one does form. So this gives us a way of saying it's not possible for a time-like singularity to form behind a horizon on basically order 1 time scales. We can't talk about what happens at later times for the black hole interior, but it does give us some small amount of progress on strong cosmic censorship. Now, a little bit about what ADS, so the role that ADS played here. So the assumption that we really need are equivariance. Again, that is the most prominent one. And also we need to assume the simplicity of the bulk boundary map at times when you have this time band on the boundary where you can talk about the past and future, the slice being both in the past and in the future of that time band, finite time band. So these are two assumptions. They're assumptions which are true in ADS CFT. They might be true in some other relation between semi-classical theory and non-perturbative description. So if these are valid in, say, a version of asymptotically flat space, if some kind of a dictionary asymptotically flat space, if these are valid there, then our conclusions will hold as well. Now, we might hope that, so this is for asymptotically flat space, this might work. I'm not sure how it would work if these are true in that case, but it could in principle, because asymptotically flat space has its own notion of time evolution. Closed universes are more problematic. So in a closed universe, the Hamiltonian is 0. Is there such a thing as a continuous time evolution? We could talk about equivariance. Maybe not, but on the other hand, there's also been a lot of progress recently arguing that the inclusion of an observer gives you an essential clock in de Sitter and also in general closed universes. So if that's the case, if that's truly necessary to talk about contentful quantum gravity in de Sitter, there might be a notion of time evolution and there might be a notion of equivariance. So there's some question to be asked potentially about whether some of this could also hold in closed universes. All right, so the upshot and then question.
On the closed universe point, you also, to blow up the perturbation, you use the n to infinity limit.
In perturbations in what?
Like when you had the delta B to show that it wasn't consistent, you
Yes.
used that it was expressed as n goes to infinity. Could that also be, like, I mean, I realize not the same argument we're told, but in a closed universe, is n necessarily?
Yeah, so in a closed universe, I don't know what the bulk to boundary map is.
Yeah,
There's no
yeah.
boundary, right? So, but you could think of the bulk to boundary map as just a map between the semi-classical effective theory and the quantum description of the system. And then you could imagine, doing perturbations to the map. So in principle, that part I'm less concerned about, although I don't know what it would mean for the slice to have this. I don't know if it's reasonable for the slice, if you have it take some slice and you say, okay, this slice is fully lives in the time, there's no time band anymore. So unless we're talking about the perspective of the observer, so maybe if the slice lives sort of in the past and future of an observer for some finite time, this is something that we could see in de Sitter, in a closed universe. But I mean, I don't know, I'm sort of speculating here. I don't know if it applies to closed universes. That does not answer your question.
Well, if. No, I can.
You sure?
Yes, yeah.
Okay. All right. Okay, so the upshot, black hole typicality, I would say is essential for decades of work in quantum gravity to be valid. We all think, well, all of us, most of us think that it's just a true statement. And this relies on what I've said before is an unjustified assumption, which is not supported by evidence from classical GR, which does allow typical states to have naked singularities and not black holes. So a resolution of the problem requires a definition of a singularity that isn't purely classical. We need to define it in a way that allows us to make some contact with the underlying quantum gravity theory. And we did that. We defined a singularity as the breakdown of the ability of semi-classical effective field theory to make predictions rather than to do actual full-time evolution. And the motivation for this was really in order to be able to include situations like the D-brane and the Oriental fold, which appear to be reasonable and should not be excluded. And we proved under the primary assumption of equivariance of the dictionary between the semi-classical theory and its full fundamental description that the breakdown of predictability can only be typical if it happens after event horizons have already formed and the consequence of event horizon formation, and not something that happens on its own. All right, thank you very much for your attention.
It's question about this predictability. You're talking about short time predictability.
Absolutely.
And now this short time remains finite, is uniformly bounded in n.
Yes, absolutely.
That's
Yeah.
in the limit. No,
so
infinity,
for the naked singularity, it sort of matters less because we're talking about short time from when you start the initial data slice. So you can start the initial data slice anywhere you want. And so this tells you you can't have a naked singularity kind of anywhere, because you say, oh, suppose a naked singularity forms at a time which is, polynomial in n after some early event. Then just take an initial data slice that's, an order one time before the naked singularity has formed. And then you execute the argument at that later time. As long as we're not talking about exponentially late times, where I don't really know how to define a lot of things, then we can repeat the argument at poly times, as long as we are talking about a short time step from when the initial data is.
But this short time is finite in the larger limit.
You mean the one,
Because you need a
The-
simple map and some notional simplicity.
so you mean the one that I choose,
Yeah, the two slices, yeah,
this one?
yes.
Absolutely. But I could talk about, if I wanted to, I could also talk about the, evaporating black holes. And I could say, okay, this is a very small time band over here,
Mhm.
right? The question is where you want to start counting from. Whereas for the black hole interior, I can't make that argument for the sort of the naked singularity I talked about here, because I need the initial data slice to be outside of the horizon. So that's where I start running into problems.
So then, if I understand well, your argument applies also to null singularity. In case
What's right?
null naked singularity.
A null singular, those are wrong, okay. So I have a null singularity, do this. Let's say, so something like this,
Yeah, you have a firewall that forms sometimes after the black hole has collapsed.
yeah, so,
You have a transparent horizon that becomes.
you want to
opaque.
talk about firewall, is what you want to do.
Maybe late time, any glass becomes opaque
Yeah.
with time, so you have this horizon that becomes a firewall sometime
Yes.
after the formation of the horizon.
Absolutely, yeah, so we could talk about, okay, so what we could do in a situation like this is actually, we could rule this out until times when it sort of approaches the asymptotic boundary. So if it's a horizon, then it's never going to reach the asymptotic boundary because it's on I plus. But if it's an actual naked singularity, eventually it'll actually reach the asymptotic boundary at finite time, so I plus will be somewhere up here. And in this case, we could rule out sort of this chunk of the singularity, but once it gets very close to the asymptotic boundary, then we're gonna have a problem, because ruling that out involves using equivariance. And we can't really use equivariance anymore if we don't know how to time evolve past this. So I think the issue, so the null I think we can deal with. The issue are space-like singularities that kind of end on the asymptotic boundary. These we don't know how to deal with, because to get a contradiction, we need to time evolve through this.
And so there is one type of null singularity that reaches the boundary, and that's bubble of nothing. Yeah.
Yes,
So those presumably are still allowed by your argument?
Yeah. Absolutely. Yeah.
I got a little bit lost about in the case of strong cosmic censorship.
Mhm.
So usually this is a state in a way that if you have either an asymptotically flat or a compact Cauchy surface, this is basically an obstruction for extensibility, right?
Mhm, yeah.
So your comments applies for asymptotically flat Cauchy or also for a
So
compact.
my comments apply to any scenario where it's a quantum version of strong cosmic censorship. And it applies to any scenario where you have a quantum gravity description of the system, which is equivariant with the semi-classical effective description. And where you have this nice simple map at early times, then before the black hole is formed, if you consider the situation of the black hole. And if you have an asymptotically flat space description that admits this, then yes, it would be a comment about asymptotically flat. Otherwise, you can formulate strong cosmic censorship in ADS. Just by you can formulate also in de Sitter, right? You can formulate it in and like weak cosmic censorship, it's not particularly asymptotics dependent. So we could formulate in ADS, and then I can certainly argue that in ADS, black holes should not have time-like singularities that form in essentially an order one time behind the horizon. And that's not the full statement of strong cosmic censorship, of course, but it's sort of a partial, a mild version of it.
I'm still a little bit puzzled by this genericity of the examples that you gave.
Yeah.
Generic in the sense that if you take an initial Cauchy surface, you have an open set in the LP topology.
Yeah.
So it's really not open just in a subset of parameters. It's really.
So it should be an open set in the space of solutions, full stop, not just a codimension. So to qualify as generic, you need to actually be able to perturb it in any direction and find that it preserves the structure. Yeah, so for example, for the Einstein-Maxwell examples, they certainly did that. They considered a perturbation of all of the parameters. And they found that it persisted. For the scalar collapse in ADS4, that was also done, right? There were like several parameters in the problem and all of them were varied.
Yeah, but that's not enough. You really need to vary the initial data on a Cauchy surface.
Yes, absolutely.
Saying that.
So you pick some initial data and then you say, you consider various, you basically consider an open set of perturbations to that full initial data. That's right, yeah. So I think, I guess I can't vouch for the Einstein-Maxwell example, but in the scalar case in ADS4, that was in fact done. It literally all it was building an initial data slice. So for the Einstein-Maxwell examples, it's a little more complicated because it started on the boundary and then it kind of evolved in. But for the ADS4 examples, those were literally built from an initial data slice. For the scalar examples, those were built by constructing an initial data slice and essentially just varying everything on it. So I would argue those were actually legit counter examples in terms of being a generic open set.
Finally, in these examples, there is a negative singularity. Is there a trapped surface?
There is a trapped surface in the scalar ADS4 case.
I mean, is there something like an apparent horizon for a while?
There is. So in the ADS4 case, there is the scalar, there are trapped surfaces. In fact, that's how the naked singularity is diagnosed. You basically, what you do is you look at the Penrose inequality. The Penrose inequality guarantees for you, if it's satisfied, trapped surfaces lie behind horizons. You find the Penrose inequality is violated on this initial data slice, and then you say, okay, so if there are any trapped surfaces on this data slice, they must lie outside of horizons, and then you find a trapped surface. So that's how it's so we can't, of course, generate the event horizon. That requires time evolution for infinite time. But the Penrose inequality is something we can check in finite time that guarantees for us that trapped surfaces will lie outside of horizons.
Okay, let's thank Netta and we can ask more questions.